How can you measure the thermodynamic stability of biomolecules or the strength of interactions, for instance? In fact, you have an experimental method that can be used to do that, and this experimental method is microcalorimetry. So what can you do with microcalorimetry? Here you have some examples. So here you can, for instance, study protein ligands interactions. So, for instance, interaction between an enzyme and its substrate, or interactions between protein and nucleic acids, and so on. You can also study protein-protein interactions. That's another example. You can evaluate and measure the protein stability, the thermodynamics of folding, identify incorrectly folded proteins. You can also study drug receptor interactions, but in this case it's quite similar to the protein ligand interactions, and so on. So that's what you can do with microcalorimetry. And of course you can also study thermodynamics of non-covalent interactions in solution. So now, which kind of experiment can you do with microcalorimetry? In fact, you have two different type of methods. The first one is called ITC, for isothermal titration calorimetry. And I will explain what is ITC in a few minutes, but in summary, it will measure the heat emitted or absorbed during a reaction between molecules in a sample and molecules that are injected. But I will explain that in a few minutes. The second method is DSC, for differential scanning calorimetry. And in this case, it measures the difference in heat required to increase the temperature of a sample compared to a reference as a function of temperature. So first, ITC. So here, what is the general principle of ITC? You see here a schematic representation of ITC. So what do you have here? Here in this cell, for instance, let's consider that I will study the interaction between a protein and its ligand. In this cell, you will have the protein in solution. So here you have only the protein in solution. Here you have the reference cell, and in this reference cell you have also the protein in solution. And what is important here is that the conditions in the two cells are exactly the same. So here the concentration of the protein, the pH, everything is exactly identical between this cell and the reference cell. And here you have the ligand that you will inject in this cell. And here your aim is to study the protein ligand interaction, and what you will measure, what you will do first is to inject here the ligand. The ligand here will interact with your protein in solution. Due to this interaction, you will have an absorption or an emission of heat, and here the apparatus will measure the power needed to keep the two cells at the same temperature. So here, let's consider that the protein ligand will emit a certain quantity of heat. Here, the apparatus will measure the power that is necessary to keep the two cells at the same temperature. So that's what ITC will do. And so here what you will see is that at each pulse of ligand, so at each injection of ligand, you will have a certain quantity of power that is needed to keep the two cells at the same temperature. And here you have this curve that has been integrated. So you can measure the strength of interaction, but you can also study the stoichiometry, and you can deduce the stoichiometry of the interaction. So what do I mean by the stoichiometry of the interaction? You see in this example, you have one protein that interacts with one ligand, and you have one binding site here. So here the stoichiometry is one protein for one ligand. But in other cases, you could have two binding sites in the protein, and you could have an interaction between one protein and two ligands to form here a complex of the protein and the two ligands. That's another stoichiometry. So that's for ITC. Okay. Yes, here you have a small movie that show you what happens when you inject the ligands in your cell here, and here you have the different the power that is required to keep the two cells at the same temperature. Okay, so here you have some information, some general information about the conditions to use ITC. I will not comment that here in this video, but you can read that for your information. Yes, just one comment. It's about the fact that you must take into account the protonation, unprotonation effect. So what do I mean with this sentence? So what is protonation, unprotonation? Protonation, unprotonation is related to acid-base reactions. So if you have a look at the 20 different amino acids that are used to compose proteins, in fact, among these 20 amino acids, some of them are acidic amino acids or basic amino acids. So here an example, you have a protein. Let's consider that at the surface you have an aspartic acid. The aspartic acid, if I write here only the side chain, it's CH2COO minus. So that's an aspartic acid at pH 7. And the aspartic acid, as you hear that in its name, in fact, it's an acidic group. And so you can have an acid-base reaction with aspartic acid, and here this aspartic acid can react with an H+, and you have an equilibrium here, and you could have obtained this COOH. And this is a protonation, unprotonation reaction. So the H+ is a proton. Here you see that you have a CH2COO minus. So you don't have a proton, you don't have an H+ on the COO minus. And so here you have the unprotonated aspartic acid, and here you have the protonated aspartic acid. Okay, so That's a protonation unprotonation equilibrium. And what is important is that it is also a chemical reaction, and there is also heat that could be emitted or absorbed during this chemical reaction. And so you have to take into account if you have such effect in the reaction that you study. Okay. Now, the second method, it's DSC. So in this case, the method works slightly differently. And in this case, it will measure the difference in heat that is required to increase the temperature of a sample compared to a reference as a function of temperature. Here again, I will explain that on a schematic, on a scheme on the next slide. And what can you do with this technique? You can, for instance, measure the stability of macromolecules. You can also identify the number of domains in a protein. I will explain also that. You could also determine the oligomeric state of a protein. So what do I mean by the oligomeric state? Well, is the protein a monomer, a dimer, a trimer, and so on. Okay, so the method here, well, in this case, you have again two cells. Here you have your sample cell, and let's consider that you would like to study the unfolding of a protein. So in this cell, you have, for instance, the protein in solution. Here you have your reference cell, and in the reference cell, you have only the solvent. So here, what is important is that, again, in the two cells, you must have exactly the same pH and so on. And the difference is that here, on the cell, in the cell on the left, you have only the protein in solution, and here, on the right, in the reference cell, you have the only the solvent without the protein. And here, what you will do, as explained here, you will measure the difference in heat that is required to increase the temperature of the sample compared to a reference as a function of temperature. So here, what you will do is to increase, is to measure the heat that is required to increase the difference in heat between the two cells, to increase the two cells by the same temperature. Of course, here, if you want to increase this cell, the temperature of this cell by 1 degree, you will probably need more heat than increasing this cell by 1 degree, because on the sample cell, in the sample cell, you have your protein in solution. And so what you will do is to measure the difference in heat that is required to increase both cells by the same temperature. Okay? So that's what you will do in DSC. And so typical DSC curves are represented here. And so here you clearly see one peak that will appear at a given temperature. Now, how can you, for instance, measure the number of domains in a protein? Well, how do you see that? Well, if you have a protein that is multi-domain, for instance, here you have a protein that presents a first domain, and here a protein that presents a second domain. Well, when you increase the temperature, when you increase the temperature, you know that your protein will unfold. But here, if you have two domains, the thermal stability of the two domains is not the same. And so you will probably have one domain that will unfold first and the second domain that will unfold in a second step. And so, for instance, if you increase your temperature, you will have the first domain that will unfold. You still have a folded second domain. And if you continue to increase the temperature, finally, you will obtain a protein that is completely unfolded. When you do that, and when you follow that by DSC, in fact, if you follow that by DSC, here I have the temperature, what I will see is two peaks. The first one that will correspond to the unfolding of the first domain, the second one that will correspond to the unfolding of the second domain. So that's how you can identify if there are several domains in your protein, and you can also evaluate and measure the thermal stability of each domain. You have the same phenomenon if you have an oligomeric protein. So here, if I have, for instance, if I have a dimeric protein, so in this case, I have two proteins that interact to form a dimer. Here again, when you increase the temperature, what you will observe is first the dissociation of the dimer. So here you see that in my representation, the two chains here are different. So here I have an heterodimer. And if you continue to increase your temperature, you will observe the unfolding of the of each chain. So you will, for instance, have here the unfolding of one of the protein and so on. And so here again, you can follow that by DSC. You can identify that your protein is a dimer, and you will observe several peaks that will correspond to the dissociation of the dimer, to the unfolding of one of the chain, and to the unfolding of the other chain. Here it's an heterodimer, so you have two different chains, and so probably two different peaks that corresponds to the unfolding of each chain.